Hey everyone, I'm Nick, and welcome to another episode of Parallel C++. So in this episode of the series, we're going to be talking about coordinating work between OpenMP threads using the single directive. So we often need to coordinate work between threads inside of our parallel programs. And we've already looked at a couple different ways that we can do this in OpenMP. So for example, we've seen how we can specify a critical section inside of our code, and we've also seen how we can specify that we want memory updates to be atomic. Now, another great tool in the toolbox when we're writing parallel applications and we need to do some coordination is by using the single directive. So the single directive allows us to specify that a block of code should only be run by, say, a single thread. So we're going to be looking at an example that uses this single directive through a couple different benchmarks here. So we're going to be looking at, specifically Gaussian elimination, implemented first in a serial version, then in a version using just a normal OpenMP parallel for loop, and then with one where we use a bit more manual coordination using single, but we get a little bit better performance. So let's go ahead and open up our first Google benchmark and try to understand the problem that we're parallelizing here. So like I said, we're doing Gaussian elimination here, and at a high level, what we're trying to do is create an upper triangular matrix with a diagonal of all ones. So, we use this Gaussian elimination to help solve these systems of equations that are represented by this matrix. So what we're trying to do is, like I said, get a diagonal of all ones and eliminate all the elements below that diagonal, right, in that bottom left corner of the matrix. So let's see how we can do that and how we're doing that inside of our Google benchmark here. So our setup code is pretty simple. All we're doing is creating a random number generator and then filling some vector with random floating point numbers here. So we're going to have a matrix that's 2 to the 10 by 2 to the 10 here, right? So just a square matrix for simplicity. Then we have our simple timing loop here. So for each iteration of this timing loop, we're going to copy in our matrix here, so this mn, and then we're going to perform Gaussian elimination. So what exactly goes into this Gaussian elimination calculation? So the first thing that we do is we handle our pivot elements. These are going to be the elements on that diagonal here that we want to set to 1. So what we do is we divide the elements in that row by whatever the pivot value is here. So here, right, for each row inside of the matrix, we get the pivot value and we divide all the elements in that row or elements starting at the pivot and then going to the right. We divide all those by pivot here. So that's how we get our ones for the pivot elements. Then from there, we need to do the elimination side of things. We need to eliminate all the elements in the bottom left, quadrant of our matrix here. And we do that through another for loop down here. So here, for each of the rows that we need to eliminate from, so one row at a time, we're going to eliminate all of the elements in the same column as the pivot. So we're going to go through all of the remaining rows in our matrix, and then we're going to do the subtraction here, right, to get rid of those elements and to turn them into zeros. So that's going to be our baseline serial version here that we're going to be comparing against. Okay, so let's see how we can, very simply parallelize this. First, just using a normal OpenMP parallel for loop. So here we'll open up this parallel4.cpp. The code is exactly identical as our last benchmark here, but now we've just added this pragma OMP parallel for to say that we want to parallelize this elimination process. So we might want to keep this serial, right? It might be just faster to do all of this pivot row calculation inside of a single thread, but for the elimination, maybe we want to parallelize that. So here we can just specify this OMP parallel for here. Okay, so that's going to be our simple parallelization. Let's see how we can do this with the single directive. So we can go ahead and open up this toSingle.cpp. And you can see that we have a slightly different setup this time, right? Our overall matrix is exactly the same, so still, 2 to the 10 by 2 to the 10 elements are the dimensions of our matrix. But now when we look inside of our timing loop here, our code has changed just a bit. So we're going to keep track of a global row here, right, before we launch this parallel block of code. So we're just using this pragma OMP parallel to spawn a group of threads that are all going to run this section here. And they're going to share the same integer row here to keep track of which row that we're working on now, right? Which pivot are we calculating for? So then, right, we have a loop here. So this is going to be a replacement for a for loop. We're going to keep running this loop while row is less than dim, right? So while we still have rows to process. And then after that, we have our pivot calculation, but we've marked it with pragma OMP single. So let's go ahead and take a look at the right-hand side of the screen where I have the Lawrence Livermore National Lab tutorial on OpenMP up, and specifically the section on the single directive. So it says that this single directive specifies that the enclosed code is to be executed by only one thread in the team. So this may be useful when dealing with sections of code that are not thread safe, such as I/O. Now, it also says right at the bottom down here in this clauses that threads in the team that do not execute the single directive wait at the end of the enclosed code block unless no wait clause is specified here. So what this is saying is that, basically the first thread that gets here is going to execute, the code inside of this single block here. And all of the other threads will just wait at the end of this block to continue, right? They'll wait for our single thread that is executing this code to finish before moving on. And this is actually also kind of the default behavior for our OMP for loop here. So if I pull up the this for loop that we're running in parallel, and we take a look down here inside of the clauses, you can see that it also has this no wait clause that says if specified, then threads do not synchronize at the end of our parallel for loop. So we have some implicit synchronization going on for this pragma OMP4. After our threads, each run like their section of this for loop, they wait for each other to finish here. Or complete their section of the work. So all of our threads are done once we move past this point. Okay, so we see here, right, in the single section, right, one thread calculates a pivot, then all of our threads move forward, then all of our threads work together to do the elimination for the subsequent rows in the matrix. And then finally, we have another single section here, right? So one thread will update the row, right, that we're going to be working on next. So it just does row plus equals 1. Okay, so that's what we're going to do for, this example, right? This solver for Gaussian elimination that uses this single directive here. So let's go ahead and compile these and look at their execution times. So we can go ahead and compile first 0 baseline.cbp with O3 optimizations, and then of course linking against libbenchmark and libp threads since we're using Google Benchmark. Then we can compile our parallel4.cpp with the exact same optimization options, except we're also going to enable OpenMP because we're using that parallel for loop. And then finally, we'll go ahead and compile, our version that's using this single directive here. And again, with fopenmp, O3 optimizations, and linking against libbenchmark and libp thread. Okay, so let's go ahead and look at the performance of these 3 different versions here. So we can start by running our baseline here, and it takes somewhere on the order of 60 milliseconds here, right? So that's our serial implementation for Gaussian elimination. Then we can run our parallel for loop here, and we can see that it gets a lot better here. So now we're at around 17.3 milliseconds. And if we go ahead and run our single, right, where instead of just doing this very simple parallel for, we're taking a little bit more of the work into our own hands and using the single directive to specify which parts of our code need to be serialized. When we run that, we see that we get a little bit better performance here. So somewhere on the order of 16 milliseconds compared to 17.3 milliseconds. So by writing a little bit of extra code, we were able to get a little more performance out of our parallel implementation. Okay, so that's going to go ahead and do it for this time. It's the basics of using the single directive. So it's a way to specify that we only want one thread to execute a line of code. And if we want to, it can also be a means of synchronizing all of our threads, right? All of our threads will wait until this block of code is executed before continuing, right? Unless we specify no wait. And the same goes with our for loop that we looked at. It also has this no wait clause that we can add. But that's going to go ahead and do it for this time. I'll make sure to link these two guides from this L tutorial below the video. And of course, you can find this or any of my other examples at github.com/coffeebeforearch. But that's going to go ahead and do it for today. As always, I'm Nick, and I hope you have a nice day.